Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome back to the Deep Dive. We're here to take those dense technical manuals and really boil them down for you. And if you're a student pilot, maybe staring down your PPL knowledge test right now, well, this deep dive is definitely for you. Today, we're getting into the nuts and bolts behind, well, maybe the three most critical numbers in flight: your speed, your altitude, and whether you're climbing or descending. We're talking about the Pitot-Static system. Sounds technical, I know, but it's basically the invisible plumbing that powers that key trio of instruments, our mission, to make sure you really get how simple air pressure translates directly into those numbers that keep you safe up there.
That's right. The Pitot-Static system, it's fundamental. Even for basic VFR flight, you could argue it's the most crucial sensing system you've got. And at its heart, it's actually a pretty elegant concept. It just uses two kinds of air pressure: static, which is just the air around you, and dynamic, which comes from moving through the air. Learning to fly really means learning to read what these pressures are telling you through your instruments, because these pressures, sometimes combined, sometimes separate, they're what make the airspeed indicator, the altimeter, and the vertical speed indicator work.
Okay, let's maybe unpack those two pressures first.
Yeah.
Static and dynamic. Why the distinction? I mean, if I'm just sitting still on the tarmac, what's static pressure measuring? Is it like the weight of the air? That's a perfect place to start.
Yeah.
Static pressure is, essentially the local barometric pressure. Think of it exactly like that.
Yeah.
The weight of the column of air sitting above you.
It's the ambient pressure just surrounding the aircraft, wherever it is. And the key thing, static pressure is always there. Hangar, runway, cruising at altitude, doesn't matter. The atmosphere is pressing in. It's our baseline.
Right, the constant. Okay. And then dynamic pressure. This one sounds like it needs, well, movement, effort.
It does, precisely. Dynamic pressure only shows up when the aircraft is moving through the air. It's the force of hitting those air molecules, pushing back against you as you fly. It's purely pressure due to motion. No motion, no dynamic pressure.
Okay, here's something that often trips up students, myself included back in the day. Wind. If the airspeed indicator is measuring this dynamic pressure, does like a strong headwind affect my indicated airspeed?
Ah, good question. Yes, absolutely. You have to remember, the ASI doesn't know or care about your speed over the ground. It only cares about how fast the air is moving relative to the aircraft. So if you're flying at, say, 70 knots in perfectly still air, you get a certain dynamic pressure. Now, if you're sitting still on the runway, brakes on, but facing a direct 70-knot headwind, the exact same dynamic pressure is hitting the sensor.
Okay, so the instrument reads 70 knots, even though I'm not moving over the ground.
Exactly. It's measuring the speed of the air mass flowing past the aircraft. Now, technically, for the Pitot tube to pick it up properly, the wind needs to be coming from generally ahead, less than 90 degrees off the nose. But yeah, the core idea is relative movement. Either you moving through the air or the air moving past you. Same dynamic pressure effect.
Excellent clarification. Okay, let's move from the what's to the how, the hardware. Starting with the collector of all this forward-moving energy, the Pitot tube. You called it a pressure hog earlier?
Yeah.
Well, yeah, in a way. It's the component designed to capture the total pressure hitting the front of the aircraft. That's the dynamic pressure caused by motion plus the static pressure that's always there.
Total pressure. Got it. And that total pressure goes somewhere specific.
It goes straight to the airspeed indicator. Only the ASI uses this total pressure input.
Which brings us to the pre-flight check. This isn't just ticking a box, right? For the student pilot listening, what are we actually looking for on that little tube? Right, it's critical. You need to visualize it. There's that main opening right at the front. That's where the total pressure goes in. But importantly, there's usually a tiny little hole on the back or underside. That's a drain hole.
A drain hole. Why?
Well, think about flying through rain or even just condensation. Moisture can get in. That hole lets it drain out, preventing water from blocking the tube or causing false readings. And blockages are the big concern. That's why we use pet covers when parked. Forget the cover, and you might find ice, dirt, or famously, little critters like mud dauber wasps have built a nest inside.
Yikes. Okay, so what happens if that tube does get blocked? Say, the main inlet is blocked, but the drain hole is open.
Ah, classic scenario.
Yeah.
Blocked inlet, open drain. The dynamic pressure can't get in, but the trapped static pressure can leak out the drain hole. Your ASI will likely drop to read 0, regardless of your actual speed.
Okay, 0 airspeed. Not good. What if both the inlet and the drain hole get blocked, say, by ice?
That one's even more insidious. If everything's blocked, the pressure trapped inside the Pitno line can't change. But as you climb, the outside static pressure decreases. This creates a pressure differential that makes the ASI behave like an altimeter. It indicates higher airspeed as you climb and lower as you descend. Extremely dangerous.
Wow. Okay, definitely see why checking that tube is non-negotiable. So the Pitot tube feeds total pressure to the ASI, but you said the ASI is the only instrument using it. How does it isolate just the speed part?
Yeah, this is where the clever engineering comes in. Think of the ASI like a little pressure balancing machine. It's designed to automatically subtract the static pressure. So total pressure, static plus dynamic, pushes on one side of a diaphragm inside the instrument. But crucially, pure static pressure, taken from the static ports we'll discuss next, is fed to the other side of that same diaphragm, or into the instrument case surrounding it.
Ah, so it pushes back with a static pressure component.
Exactly. The static pressure effectively cancels itself out because it's present on both sides of the equation. What's left? Only the dynamic pressure is left to actually move the diaphragm and the needle. Change in dynamic pressure equals change in indicated airspeed. Simple as that, mechanically speaking.
A little mechanical mathematician in the dashboard. Okay, so the ASI sorts out the dynamic pressure. What about the other two big ones, the altimeter and the VSI? They don't need the Pitot tube at all.
Nope, they run purely on static pressure. They need that baseline atmospheric pressure we talked about earlier.
And where do they get that from?
They get it from the static ports. These are small, flush-mounted vents, usually on the side of the fuselage, sometimes on both sides. Their location is really important. They have to be placed where the air flows smoothly, what we call free and undisturbed air. You don't want turbulence or weird pressure changes near the port itself, as that would mess up the reading. The static pressure is then piped through tubing directly to the altimeter and the VSI.
Okay, let's peek inside those two instruments then. How does static pressure tell us altitude?
The altimeter is basically a sensitive barometer. Inside, it has these sealed accordion-like capsules called aneroid wafers. They're calibrated to a standard pressure, like 29.92 inches of mercury at sea level. As you climb, the outside static pressure decreases. Less pressure pushing on the wafers allows them to expand.
Like a little balloon inflating slightly.
Exactly. And as you descend, the static pressure increases, squeezing the wafers, making them contract. This physical expansion and contraction is mechanically linked through gears and levers to the needles on the altimeter face, showing your altitude.
Makes sense. And the VSI, the vertical speed indicator, how does that use static pressure to show rate of climb or descent? It feels a bit different.
It is slightly different, yes. It also has a diaphragm that gets direct static pressure. But the key is how the case surrounding that diaphragm is vented. The instrument case is also connected to the static source, but only through a very tiny, precisely sized hole called a calibrated leak.
A calibrated lead. Okay.
So imagine you start climbing. The static pressure drops quickly inside the diaphragm because it's directly connected. But the pressure inside the instrument case drops much more slowly because it has to leak out through that tiny calibrated orifice.
Ah, so there's a temporary difference in pressure between the inside of the diaphragm and the case around it.
Precisely. And that pressure difference is what moves the VSI needle. It's literally measuring the rate at which the static pressure is changing. If the pressure difference is large, fast change, you get a large climb or descent indication. If it's zero, stable pressure, the VSI reads 0.
Okay, that's clever. Measures the rate of change. Now, this brings us to the what-if scenarios. Thinking defensively, like a PPL student should. What if that static port ices over or gets blocked by, I don't know, tape someone left on?
A blocked static port is serious. If the static pressure can't get into the system or change, then, well, your altimeter will freeze at the altitude where the blockage occurred.
Stuck reading whatever it was.
Yep, and your VSI. Since it relies on sensing a change in static pressure, it will settle back to read 0, even if you're climbing or descending. Very misleading.
So frozen altimeter, 0 VSI. But what about the ASI? It uses static pressure too for that balancing act.
Right. With a blocked static port, the ASI will still work, but it will be inaccurate. If you climb above the altitude where the blockage happened, the ASI will read lower than your actual airspeed. If you descend below it, it will read higher, because that trapped static pressure is no longer correct for the altitude.
Okay, so blocked static port equal unreliable altimeter, VSI, and ASI. That sounds like a bad day. We need a backup plan.
And that's where the alternate static source comes in. On aircraft equipped with one, it's usually a little valve or a pull knob somewhere in the cockpit.
But pulling that does what exactly?
It basically disconnects the instruments from the potentially blocked external static port and vents them instead to the air pressure inside the cockpit.
Okay, use the cockpit air as the static source. Seems logical. But is the pressure inside the cockpit the same as outside? I feel like there's a catch.
There is, and it's a crucial one for pilots to understand. The pressure inside the flight deck is almost always slightly lower than the true ambient static pressure outside.
Lower. Why?
It's due to airflow around the fuselage. As air speeds up to flow around the curved shape of the cabin, its pressure drops. That's the Venturi effect. The slightly lower pressure outside tends to, well, suck air gently out of the cabin through any small leaks, lowering the internal pressure.
Okay, the Venturi effect lowers the cockpit pressure. So if we use that lower pressure for our static source, what errors does that introduce? This sounds like check ride material. Absolutely is. You must know these errors. Okay, 3 main things happen when you use the alternate static source.
The altimeter. It senses this lower than actual static pressure. Lower pressure normally means higher altitude, right? So the altimeter will indicate you are higher than your actual altitude.
Right. You think you're higher than you are. Dangerous near terrain.
The airspeed indicator. Remember, it subtracts static pressure from total pressure. If the static pressure value it's using from inside the cockpit is artificially low, it doesn't subtract enough.
This means the remaining pressure difference seems larger. So the ASI indicates an airspeed greater than your actual airspeed.
So you think you're going faster than you really are? Also dangerous, especially near stall speed.
Exactly. And 3, the vertical speed indicator. This one's more momentary. When you first select the alternate source, that sudden input of lower pressure makes the VSI briefly show a climb before it stabilizes, assuming you're holding constant altitude. Okay, altimeter reads high, ASI reads high, VSI shows a momentary climb.
Got it. These aren't just small errors, are they?
They can be significant enough to matter. And that's why the crucial step, if you ever have to use the alternate static source, is to immediately consult your aircraft flight manual or pilot's operating handbook.
The AFM or POH? Why?
Because in that book, there will be a table or correction card telling you exactly how much higher the altimeter and ASI will read at different altitudes and airspeeds when using the alternate source.
Yeah.
You have to apply those corrections.
So you know the error, but the book tells you the amount of error. Okay. Now, what if your aircraft doesn't have an alternate static source installed? Some simpler trainers don't. What then? Is there a nuclear option?
There is, and it sounds dramatic, but it's a recognized procedure in some emergency checklists. If you have a complete static system blockage and no alternate source, the recommended action can be to break the glass face of the vertical speed indicator.
Break the VSI glass. Seriously.
Seriously, you're intentionally sacrificing that instrument to save the others, essentially. By breaking the glass, you're venting the entire static system to the cockpit air, just like an alternate source would.
But why the VSI? Why not the altimeter?
Because the VSI is generally considered the least critical of the 3 static instruments for maintaining control of the aircraft in an emergency. You absolutely need altitude awareness, altimeter, and airspeed awareness, ASI, even if slightly inaccurate, to keep flying safely. Breaking the VSI glass will almost certainly render the VSI itself inoperative or highly erratic because you've bypassed its calibrated leak mechanism, but it should restore a static pressure reference the cockpit's ambient pressure to your altimeter and ASI.
Wow. Okay. Sacrificing the least important to get some reading, even an inaccurate one you have to mentally correct for, on the 2 most critical. That makes a grim sort of sense.
It's definitely a last resort, but it provides a way to regain basic situational awareness regarding altitude and speed. Okay, so let's tie this all together for the student pilot listening. The bottom line seems to be, the Pitot-Static system is about 2 pressures. Dynamic pressure from motion is balanced by the ASI to give you speed.
And static pressure, the ambient air, directly drives your altimeter and VSI. Understanding how they work, and crucially how they can fail, is fundamental.
Absolutely. These instruments, powered by simple air pressure, are your eyes when you can't see the horizon or the ground. Knowing their limitations, especially with blockages or using the alternate source, is key to safe flight. And it leads to an interesting thought. We just talked about the VSI being the least important in that dire static failure scenario. But let's think bigger picture. Imagine an emergency, maybe low visibility, maybe partial panel failure. You need speed control to avoid stalling, and you need altitude control to avoid hitting anything. If you had to argue which single piece of information, reliable indicated airspeed from the ASI, or Lyell indicated altitude from the altimeter is the absolute most critical for immediate aircraft control and survival in that moment? Which would you prioritize? Something to maybe mull over as you study for that check ride.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.